Hello engineers, welcome to Civil Nirman. In the previous session, we have understand what is a compression member, how it behaves, also various parameters like buckling and slenderness ratio which affects its design strength. Now, in today's session, we gonna understand the codal provision part from IS 800 2007. IS 800 2007, in that section 7 gives you the design guidelines for design of a compression member. So in this session we gonna understand the parameters which will help to calculate the compression strength of the member. Also we will go thoroughly each of the equation with complete parameter understanding. So stay tuned with us. So section 7 on page number 34 of IS 800 2007 gives you the guidelines for the calculating the design compressive strength of a particular member. So let's start first with the clause 7.1. So what specifies 7.1 clause? See, common hot rolled and built up steel members used for carrying axial compression usually failed by flexural buckling. So in the previous session we have understand the behavior and the buckling modes. The buckling strength of this member is affected by three parameters: residual stresses, initial bow and accidental eccentricities of the load. So as I discussed, residual stresses are primarily caused during the manufacturing process of these hot rolled steel sections. So during the process of the cooling, it will experience temperature variation while they are in the process of cooling down. Next one is the initial bow. Now let's understand through an example. So what is this? So in this figure, consider these two columns in which one is straight and the load is applied at the center. Right? Now second picture, in this you can see that it is already buckled due to the imperfection and the load is slightly shifted right from the centroid. So for this second column, as it is already deformed, the capacity will definitely reduced and with less load it may buckle compared to the first one. So this is the local bow imperfection and it is considered during the compression capacity calculation with the other factors. So these three factors are majorly impacting its capacity. Now all these imperfections are specified in table 7, which again depends on the buckling class. So we will check out these parameters further in this session. Now see, for the I section, depending upon the overall dimension of the section and whether the section is rolled section, hot rolls, whether the section is hot rolled or welded, buckling class is determined for the major and minor axis and it is used to calculate the imperfection factor, and it is further used to calculate the compressive strength FCD and design capacity value. Now we will summarize this everything. So let's get back to the presentation part. So now you understand that the design strength is mainly affects these three parameters. We have understand the residual stress, that is the temperature variation or differential cooling you can say. We have understand the initial bow, right? And the third one is the accidental eccentricities of load. Accidental eccentricity means the load is not completely acting at the center of the member. It will be slightly away from the axis, right? So due to all these your strength will get reduced, and we need to incorporate all and we need to consider all these parameters as well while designing a member. To account for all these factors, basically what code is doing, so to calculate the strength of the member, first of all you need to identify the buckling class. So code has divided the various categories of section, let's say I section, which is hot rolled, or it can be a built up section, channel section, angle section. For various categories of section, code has specified the category of this buckling class A, B, C, D, which you can refer in table 7. So from where you have to first identify the section that in which category of buckling class it falls. and based on that you can work out the strength part. So clause 7.1.2 gives you the equation to work out the design compressive strength PD of particular member. What it specifies? P less than PD. So here, what is P? So P is basically your factored axial load which your compression member is experiencing, and PD is the design compressive strength. So here it specifies P should be less than PD, right? So your design load should be higher than the actual factored load which your column is experiencing. Now further, it specifies the equation PD as AE into FCD. Now what is AE? AE is the effective sectional area which is defined again in 7.3.2. So FCD is the design compressive strength obtained as per 7.1.2.1 clause. Now let's understand the workflow, how it works. So here I have summarized few things for you. So as code suggests the equation PD equals to AE into FCD, first of all I want you to understand each parameters and its intercorrelation. Later on, one by one, we will understand each of these parameters from the code part. So first, as specified, the design compressive strength you can work out utilizing this equation, where you have to work out AE, that is effective area, and the FCD part. Now see, there are three ways to calculate this FCD. So first, remember this workflow and its correlation. Later on, we will understand each of the parameter thoroughly in the upcoming part. So basically you can work out FCD, that is your compressive stress, using equation that is specified in your code, page number 34. This gives you the equation part. Second option is you can work out FCD value from table 9, which is specified on page number 40. So if I give you a highlight over here, you can work out the FCD value from this table as well, which ultimately gives you the compressive stress FCD value for a particular column class. As I mentioned, there are 4 classes. For each class this table is specified, which ultimately depends on your slenderness ratio. Now one important thing to observe over here, see, the KL by R ratios are given from certain intervals, let's say 10, 20, 30, 40, and let's say our yield stress of the member is usually 250. So if I compare this two, right, so as you can observe, as the KL by R values are increasing starting from 10, 20, 30, 40, 50 and so on, you can observe that for the yield stress of 250, the FCD value will start decreasing. So this is one of the important part. So from this relation you can identify that higher the slenderness ratio, your yield stress will decrease. So as the slenderness value will be lower, you will get more yield stress. So this one is the first relation that you need to understand. Now let's get to second one. Second one is table 8 Xi, which is specified on page number 36. So in a similar manner, the tables for all these 4 classes are specified over here in the form of table 8. So in the same manner, again you can work out the value of our different buckling classes, which depends again on KL by R, and for the same segment you can work out the Xi factor for column, and you can observe the same behavior here as well, right? So I hope you are clear with this 3 part: the equation part, slenderness ratios relation with respect to your Fy, and Xi. Now let's understand this, that you, in order to work out the FCD, you have to work out this equation first, that is Fy divided by gamma m0. Further, it divides with the equation of phi plus in the square root of phi square minus lambda square, and again it's specified with the equation Xi into Fy divided by gamma m0. right? So further, in order to calculate phi, again code gives you the equation 0.51 plus alpha in the bracket lambda minus zero point 0.2 plus lambda square, and lambda is what? That is non-dimensional effective slenderness ratio, which gives you again the equation in terms of square root Fy upon FCC, where FCC is the Euler's buckling stress, pi square E divided by KL upon R. Now try to understand these correlations, right? And try to interconnect this. So what will be the steps? So in order to work out the FCD value, first of all you need to work out all these parameters. Now see, we will go one by one with the clear understanding of all these parameters, but first I want to understand the relation, and in the upcoming part I will explain each parameter briefly. So first of all, understand this. So from this workflow, these are the steps, right? First of all, what you have to do from this flow chart, you can definitely understand that in order to work out FCD value, we need to start from reverse, right? So step 1 will be what? You have to calculate the slenderness ratio, effective slenderness ratio, right? Step 2 will be what? You need to determine the buckling class. So buckling class, in order to determine the buckling class, code is giving you another table, that is table 10 here. Sorry. So from here you can identify for the rolled eye section or for the welded section, you can determine the buckling class. We will go into detail further, right? So based on buckling class, using table 10, you can identify the value of alpha, right? So once you work out alpha and the slenderness ratio, you will able to get the phi value. Now try to understand the correlation again. You can observe that these 4 buckling class, as you go further from A, B, C, D, the values are increasing, right? So again, now this alpha that is in the addition of this phi's equation, right? So as if you have the higher buckling class, the phi value will get increased. Now see, this phi is inversely proportional to the FCD value. So ultimately, if you have the higher value of the buckling class, right, so it will add it up over here and your value of phi will increase, and as your value of phi will increase, your FCD value will get decreased, which ultimately affects your compressive strength. So higher the FCD value, your compression strength will be higher, and lower the value, the strength will be lower, right? So ultimately, if you get the lower class, let's say class from class A or B, it has lower value, so the phi value will start decreasing. As it decreased, FCD will increase. So you have to remember this correlation so you can quickly identify, right? So once you work out the phi value, you can just find out this FCD easily, right? And once you find out the FCD value, then code is suggesting you to check this relation, right? That your FCD should be less than or equal to Fy upon gamma m0. So this check you need to perform. Now let's understand each parameter thoroughly from the code. Let's move on to the equation part in detail. So in order to calculate PD, as I suggest, we have already understand the workflow. You have to work out the AE into FCD, right? Where AE is what? Effective sectional area, which is defined in 7.3.2. So let's understand what clause 7.3.2 says. So it specifies, except as modified in clause 3.7.2 class 4, the gross sectional area shall be taken as the effective sectional area. What does it mean? That you can take AE, sorry, my bad, I have to write it specifically. E equals to AG, right? It specifies the gross sectional area shall be taken as the effective sectional area. AE can be taken as AG, that is gross area, for which category? That for all the compression members fabricated by welding, bolting and riveting, so long as the section is semi-compact or better. That means the section should be either semi-compact or in the upper class. Now see, we have 4 classes: class 1 plastic, 2 compact, 3 semi-compact, and the 4th one is slender. That's why it's specified except as modified in class 4. So apart from class 4, that is slender section, class 4, that means in order to take effective area as gross area, your section should fall under these 3 classes, that is plastic, compact and semi-compact. It should not fall under the slender class, right? Now see, we have 3 methods: compression members fabricated by welding, bolting and riveting, right? So our section should fall under these 3 class. Now see, compression member can be fabricated by welding, bolting and riveting. Now as you know, except welding, in the bolting and riveting part we have bolts, right? So for that again it specifies the guidelines that the holes not fitted with the rivets, bolts or pin shall be deducted from gross area to calculate the effective sectional area, right? Now what does it specifies? That for these 3 category of the sections, and if your member is fabricated by welding, bolting or riveting, you can take your effective sectional area as gross area in case of the compression member. That means you do not have to deduct the bolt part. Why? Let's just understand. Now if you remember, in case of the tension member part, what basically you were doing, that let's consider this through an example. Let's say this particular member is in tension. So in the tension member part, what you are doing, then let's say if we have 8 bolts like this in this arrangement, and if you have bolts, then in order to calculate the effective area, what you gonna do, in the tension part you deduct the bolt hole area, right? But in case of in the compression part, code is suggesting not to do that, right? Why? Because see, in the tension member part, your member is experiencing tension in the opposite direction, but in the compression part, what is happening, your load will be acting along the axis of the member, right? And if you have bolts, so let's say for this particular segment, if it is experiencing the compression, right, and if you have bolts here, so these bolts will help, right? If you have bolts, these bolts will help in the compression loading part, okay? But in case of tension member, it is not the case. So the gross sectional area for all compression members fabricated by bolting, welding or riveting, that means in this case bolt holes did not to be subtracted as long as the section is semi-compact, okay? You have to keep in mind, or it can be, or it should be better than semi-compact, but it should not be slender. So holes are not deducted as the area is filled with the bolt diameter, and hence the load is distributed over the gross area, right? So it is contributing in the loading part. Now however, if the holes in which the rivets, bolts are not present, right, so in that case you need to deduct that part. So let's say here I have considered these 4 bolts. Let's say this is a compression member, I have considered these 4 bolts and there are remaining 4 holes, or let's say we have bolts in all these 6 places, but we don't have any bolts in this 2 part. So for these 2 area you have to deduct. That's what code specifies. Let me just take you to the part again, right? So holes not fitted with the rivets, bolts or pins shall be deducted from the gross area to calculate the effective sectional area. Otherwise you can consider effective area as gross area. So that's the major important part you need to understand here in the effective sectional area portion. So I hope you are clear with the AE part. In the next session we will discuss in detail about the FCD. Stay tuned for the next lecture. Don't just learn software, learn concepts.